A shock wave moving at 1,293 kilometers per second just left the sun. That is more than 4 million kilometers per hour. And part of the coronal mass ejection driving that shock is now, according to NOAA modeling, pointed directly at Earth with an arrival window that opens late Saturday into Sunday. This eruption came from a single active region on the solar disk, one cluster of sunspots, and that one region fired 2 X-class flares in just 8 hours, the most powerful class of flare that exists, on top of a broader swarm of weaker flares it had been throwing off all day. And a full day before that, the same region had already launched a first coronal mass ejection toward us. That one is already on the way. And here is where it gets interesting. When a faster cloud of plasma is launched behind a slower one, it can catch up, it can slam into it, it can swallow it. Scientists call this CME cannibalization. And when it happens, 2 moderate events can merge into one far more dangerous storm. By the end of this video, you will understand exactly what the instruments detected, why the shock speed matters, what NOAA is forecasting for the weekend, how serious the geomagnetic storm risk really is, without the panic and without the hype, what the viral videos on this topic get wrong, and why the bigger concern may not be what is heading toward us right now, but what is still rotating into our line of fire. Welcome to the Space Desk. Let's get into it. Let's start with the facts. With what was measured, not with what somebody felt. The Sun is right now in the active phase of its 11-year cycle, the 25th since continuous record-keeping began. And rotating across the visible disk is an active region where the magnetic field is twisted, compressed, and overstressed to the point where it simply snaps. When a field like that violently reconfigures, it releases an enormous amount of energy, by some estimates the equivalent of billions of hydrogen bombs detonating at once. And this particular region produced not one flare, but a whole series in the last day. 2 of them were X-class. To put that in perspective, flares are classified by their X-ray output using the letters A, B, C, M, and X, and each letter up the scale is a 10-fold jump in power. C is the background hum of an active sun. M is already serious. And X is the top of the scale, the most powerful flares the sun is capable of producing. This region delivered 2 of them in 8 hours. That is not a coincidence. 2 X-class flares in 8 hours from a single source is a sign that the region is magnetically very unstable and still recharging. It fired, recharged, and fired again. And that behavior, on its own, is a warning. It helps to understand why some regions do this and others sit quietly. Sunspots come in magnetic flavors, classified by how tangled their polarity is. A simple region with one clean positive pole and one clean negative pole rarely does much. But when a region develops what's called a delta configuration, opposite magnetic polarities cram together inside a single sunspot, separated by a sharp dividing line. The field there is sheared and stressed like an overwound spring. Those are the regions that produce the big flares. And there is a second distinction that matters enormously for us on Earth. Not every flare launches an ejection. Some are what physicists call confined flares, where the magnetic field flexes, releases its energy as light, and snaps back into place without throwing anything into space. Others are eruptive, where the overlying field gives way and a chunk of the corona is flung outward. A region that produces eruptive X-class flares, twice, while rotating across the disk, is the kind of region a forecaster circles on the map and does not take their eyes off. The flare itself is a burst of light and X-rays. It reaches Earth in 8 minutes, at the speed of light, and its immediate effect is what we call a radio blackout. The X-rays ionize the upper atmosphere on the day side, and shortwave radio, the kind used by long-haul aviation, mariners, and emergency services, can drop out for tens of minutes. NOAA measures this on a separate scale, R from R1 to R5, and a strong X-class flare can cause an R3 or higher blackout across the entire sunlit side of the planet. But the flare is only the flare in the sky. The real threat is what often flies out alongside it: the coronal mass ejection. A coronal mass ejection is when the sun hurls not light, but matter into space. Billions of tons of superheated plasma, charged particles, and with them a chunk of the sun's own magnetic field. It is not a beam. It is a cloud. A gigantic cloud of magnetized gas that tears away from the sun and barrels across the solar system. It's worth picturing what that cloud is actually built like, because the structure is the whole story. A classic ejection has three parts: a bright leading edge of swept-up material, a dark cavity behind it, and at the heart of it, a twisted rope of magnetic field, what physicists call a flux rope, coiled like the core of a giant magnetic spring. That flux rope is the dangerous part, because it is the piece carrying the organized magnetic field that will, or will not, lock onto Earth's. And ahead of the whole structure, when the cloud is moving fast enough, rides the shock, with a region of compressed, turbulent solar wind piled up just behind it called the sheath. Keep that word in mind, the sheath, because it can drive a storm of its own even before the main cloud arrives. For scale, the ambient solar wind streaming past Earth on an ordinary day moves at around 400 kilometers per second. This shock is moving at more than 3 times that. It is not drifting toward us. It is plowing. And here is where that number comes back. 1,293 kilometers per second, the speed of the shock front leading the ejection. Why does speed matter so much? For 2 reasons. The first is travel time. The average distance from the Sun to Earth is about 150 million kilometers, and most ejections take 2 to 3 days to reach us, gradually braking against the solar wind on the way. But a fast ejection with a strong shock front covers that distance far quicker. For comparison, the ejection that caused the famous Carrington event of 1859 reached Earth, by calculation, in under 18 hours. The less time spent in transit, the less energy the cloud loses on the way, and the harder it hits the magnetosphere. The second reason is subtler and more important. The faster the cloud moves relative to the surrounding solar wind, the stronger the shock wave it drives ahead of itself. That shock compresses the interplanetary magnetic field and effectively determines how sharp the first blow against Earth's magnetic shield will be. Speed is not just about when it arrives. Speed is about how hard the jolt lands. 1,293 kilometers per second is very fast in the upper part of the range. Not a record. Faster ejections have been clocked, up toward 2 and even 3,000 in the most extreme events. But it is the kind of speed at which geophysicists start watching their instruments very closely. And yet, remember this: high speed by itself does not guarantee a strong storm. It creates the potential. Whether that potential is realized depends on a completely different parameter, one that cannot be measured until the cloud is almost on top of us. We will come back to it. This is exactly where most of the loud headlines trip up. Now, why this weekend situation is potentially more serious than usual? It is not one ejection heading toward Earth. It is 2. The first left a full day before the X-class flares. It is slower, it is out in front, and it is already clearing a path through the solar wind. The second, the one with the shock front at 1,293 kilometers per second, launched later but is moving much faster, and it is traveling down the same track. What happens when the fast cloud catches the slow one? It can slam into it. And then you get what's called CME cannibalization. The faster ejection literally swallows the slower one, and they merge into a single structure. Why is that bad? Because the merger compresses the plasma and the magnetic fields of both clouds into one dense, tangled, amplified structure. The fields add up and twist together, the density rises, and crucially, the odds increase that somewhere in that tangle is a long stretch of magnetic field oriented the wrong way for us. And that, more than anything, is what sets the strength of a storm. 2 moderate ejections, each of which alone would deliver a mild jolt, can merge into a single storm noticeably stronger than the sum of its parts. That exact configuration, a fast ejection chasing a slow one, was behind several genuinely major geomagnetic events in the observational record. There's a reason the merger amplifies things rather than just averaging them out. The slow cloud out front acts almost like a snowplow, sweeping the solar wind clear and carving a low-density channel behind it. The fast cloud, launched into that pre-cleared corridor, doesn't lose as much speed to friction as it normally would, So it arrives still moving fast and slams into the back of the first cloud with real force. The collision compresses both magnetic structures together, and if their fields happen to align in a reinforcing way, the combined field can be substantially stronger and more sustained than either would have managed alone. That last condition, whether the fields reinforce or partly cancel, is again a roll of the dice we can't read until the merged structure reaches us. But it is why a double CME weekend gets flagged differently from a single, ordinary event. Whether cannibalization actually happens this time is impossible to call in advance. The geometry has to line up. But the mere possibility of an amplified compound blow is what has NOAA watching this weekend especially closely. When NOAA, specifically the Space Weather Prediction Center, the SWPC, says an ejection is Earth-directed, they are relying on models. They take images of the ejection from the coronagraphs on several spacecraft, reconstruct its three-dimensional shape, estimate its speed and direction, and calculate when and at what angle the cloud will reach Earth's orbit. From that, a forecast is issued, and when warranted, a watch. How do they even see the cloud in the first place? With coronagraphs, instruments that block out the blinding disk of the sun with a small occulting disk, the way you'd raise a hand to see something near a bright lamp, and reveal the faint corona around it. When an ejection erupts straight toward Earth, it doesn't appear as a blob heading off to one side. It expands outward in every direction around the occulted sun, forming what looks like a glowing ring, a halo. A full halo ejection is the signature forecasters least like to see, because it means the cloud is coming either right at us or right away from us. And for an eruption from a region facing Earth, that means right at us. Spacecraft positioned off to the sides of the Sun-Earth line add a second and third viewing angle, letting modelers triangulate the cloud's true shape and speed in 3 dimensions rather than guessing from a single flat image. That triangulation is what turns a smear of light into an arrival time and a confidence range. The strength of a geomagnetic storm is measured on the G scale, and it is worth knowing by heart. G1 is minor. Small fluctuations in power grids, auroras at high latitudes. G2 is moderate. Grids under some strain, auroras pushing further south. G3 is strong. Possible false alarms in grid protection systems, navigation problems, auroras visible at mid-latitudes. G4 is severe. Real difficulty managing voltage in grids, degraded GPS and radio, auroras far to the south. G5 is extreme, the top of the scale. Widespread grid failures, transformer damage, auroras visible almost to the equator. Across the entire modern observing era, G5 events have been very few. For the current situation, the realistic scenario is a watch somewhere in the moderate to strong range, call it G2 to G3, with upside risk of going higher if cannibalization kicks in and if the cloud's magnetic orientation turns out unfavorable. Let me underline that. This is a range, not a verdict. And here is why no honest forecaster will hand you a precise number 2 days out. Here is the moment I asked you to remember. The strength of a storm depends almost entirely on a single parameter, called BZ, the vertical component of the interplanetary magnetic field that the ejection carries within it. Let me explain it simply. Earth has its own magnetic field, and it works like a shield. Normally, it deflects the solar wind off to the side. But if the magnetic field of the incoming cloud is oriented opposite to Earth's, if BZ, as they say, points south, the two fields lock onto each other, and the shield effectively opens. The energy of the solar wind pours straight into the magnetosphere. The storm begins. But if the cloud's field points the same way as Earth's, north, the shield holds. The cloud can be huge, fast, dense, with a perfect shock front, and still deliver only a mild jolt, because the door happened to be closed. And here is the uncomfortable truth about space weather. We do not know BZ in advance. The orientation of the field inside an ejection cannot be reliably measured until the cloud reaches a point called L1, about 1.5 million kilometers from Earth toward the Sun, where scout spacecraft like DSCOVR and ACE keep watch. As the cloud passes through them, we finally see its true magnetic field, its speed, and its density. And only then does it become clear whether the storm will be strong or weak. How much warning does that line give us? At this speed, literally 30 minutes to an hour. That is the entire real window of a precise forecast. Before that, all we have are probabilities and scenarios. And there is a further wrinkle that makes the forecast even less certain. Remember the sheath, that compressed band of turbulent solar wind riding just behind the shock? Its magnetic field is messy and constantly flipping orientation, so it can dump energy into the magnetosphere in unpredictable bursts before the cleaner flux rope even arrives. And duration matters as much as direction. A brief southward flicker of BZ gives a small storm. A long, sustained stretch of southward field, hours of it, is what builds a great storm, because the magnetosphere keeps draining energy the entire time the door is held open. So even once the cloud reaches L1, the picture keeps evolving minute by minute as different layers of the structure sweep past. Which is why the correct way to put it is this. The potential for a significant storm exists. The speed is high. There is a risk of amplification through a merger of the ejections, but the final strength of the blow will only be decided once the cloud crosses L1 and shows its magnetic face. Anyone who guarantees you a specific number 2 days out either does not understand the physics or is selling you fear. Now let's be honest about the noise around this topic. Every time the sun throws an X-class flare, the internet fills up with headlines about a solar apocalypse and civilization going dark over the weekend. Let's sort out what is true and what is manipulation. Mistake 1. Confusing the flare with the storm. An X-class flare is not a geomagnetic storm. The flare hits dayside radio and arrives in 8 minutes. The storm is an impact of matter and magnetic field a day or two later by a completely different mechanism. You can have the most powerful X-class flare with no storm at all if the ejection went the wrong way. And the reverse. The headline X flare heading for Earth is almost always inaccurate. What is heading for us is not the flare, it's the ejection. Mistake 2. Treating speed as the verdict. Speed creates potential, but BZ decides. A video screaming 1,300 kilometers per second, brace for the worst, is leaving out the single most important fact. The orientation of the cloud's magnetic field is unknown and may well turn out to be favorable. Mistake 3. Getting the direction wrong. A huge fraction of the ejections that look dramatic in the imagery are actually traveling past Earth, off to the side, above or below the plane. Even an Earth-directed ejection often only grazes us with its edge. A glancing blow and a direct hit head-on are two very different storms. Mistake 4. Promising the end of civilization. Yes, an extreme event can do serious damage. The threat is real, and we'll get to it. But that does not mean every X-class flare will shut off your refrigerator over the weekend. Between possible GPS glitch and a beautiful aurora, and collapse of a continent's power grid, lies a colossal difference in scale. The vast majority of events that trigger a wave of online panic deliver, in practice, mainly a northern aurora at unexpected latitudes, and nothing more. So what is the real story? The real story is that we have a very active region that fired at the top of the scale twice in 8 hours, that 2 ejections are pointed at us with the possibility of merging, and that one of them carries a fast shock front. That is a legitimate reason to watch the instruments and keep services on standby. But it is not a reason to panic, and it is certainly not a reason to believe someone painting an end-of-the-world picture without a single word about BZ, direction, and the geometry of the hit. To understand what the sun is capable of at the top of the scale, let's look at what has already happened. The benchmark is the Carrington event, September of 1859, the most powerful geomagnetic storm in the entire instrumental record. The astronomer Richard Carrington saw a flare on the disk with his own eyes, and less than a day later, the ejection struck Earth. Auroras blazed so far south they were seen near the Caribbean. In some places it was bright enough at night to read a newspaper. And the telegraph, the only electrical infrastructure of the era, failed worldwide. Wires sparked, operators were shocked, some telegraph stations caught fire. And here is the key thought. In 1859, we had almost no electrical civilization to break. Today, we do. All of it. The modern era. March 13, 1989, Quebec. A G5 storm induced what are called geomagnetically induced currents in the long power transmission lines. They overloaded the equipment, and the Hydro-Quebec provincial grid collapsed in 90 seconds. 6 million people were left without electricity for 9 hours in the middle of a Canadian winter. This is not theory. It happened. Then came the Halloween storms, late October and early November of 2003. A series of extreme events. One of the flares was so powerful that the instruments measuring X-rays simply maxed out. It was estimated above X28, and it remains one of the strongest in the entire observational record. A power grid in southern Sweden took a hit. Airlines rerouted polar flights, and a number of satellites suffered glitches. And finally, an event many people remember personally. May of 2024, the Gannon storm, named in memory of space weather researcher Jennifer Gannon. The first G5 storm in over 20 years. Auroras were seen where they had not been seen for generations, over southern Europe, over much of the United States. People went outside to photograph the sky with their phones, not believing their eyes. But the storm had another side. Precise satellite navigation degraded in exactly the days when American farmers were planting fields with GPS-guided equipment, and part of the planting season stalled. Beauty in the sky and real bills on the ground at the same time. That is the range this subject lives in. From a harmless aurora in an unexpected place to a province without power in 90 seconds. Which is why every fast Earth-directed ejection deserves to be watched, calmly but seriously. There's one more event that almost no one outside the field talks about, and it is the most sobering of all, precisely because nothing happened. In July of 2012, the Sun launched an ejection in the Carrington class, a true monster, with one of the highest speeds ever recorded. It tore across Earth's orbit. But it crossed the orbit at a point where Earth was not, the planet having been on the other side of its orbit roughly a week earlier or later. One of the stereo spacecraft happened to be sitting right in the path and measured the whole thing, which is how we know just how extreme it was. Researchers later estimated that had it left the Sun a week or so on, when Earth was in that spot, it would have produced a storm rivaling Carrington itself, with a modern grid in its path. We did not dodge it through any warning or preparation. We dodged it through pure orbital timing. That is how thin the margin can be. And the statistics underline it. Events of that magnitude are estimated to occur perhaps once every century or two, while smaller but still damaging storms come far more often, which is exactly why the question is never if, but when, and will we be looking the right way? Now, concretely, what can be damaged if this weekend's storm turns out to be strong? Not the abstract civilization, but point by point. Power grids are the main vulnerability. A strong storm induces those geomagnetically induced currents in the high-voltage lines. These slow, nearly direct current flows seep into transformers designed for alternating current and saturate their cores. The transformer overheats, the protection trips, or, in the worst case, it does not trip and the equipment fails. Replacing a large power transformer is a matter of months because they are built to order. Quebec in '89 was exactly this mechanism in action. Satellites. A storm heats and inflates the upper atmosphere. The thermosphere expands upward, and satellites in low orbit start dragging through denser air than they were designed for. Drag rises, orbits sink. In February of 2022, a relatively modest storm raised atmospheric drag just enough that SpaceX lost about 40 newly launched Starlink satellites, which couldn't climb to their working orbit and burned up. On top of that, there is the direct hit to electronics. Charged particles build up a charge in the circuitry and cause faults. Navigation. GPS, GLONASS, and the rest rely on the signal passing through the ionosphere predictably. A storm churns up the ionosphere, and accuracy drops, sometimes by meters, sometimes more. For a smartphone, a trivial thing. For precision agriculture, marine navigation, surveying, aviation, a real problem. Radio and aviation. Shortwave communication, which transpolar air routes depend on, can drop out during strong events. Flights over the pole get rerouted, costing extra fuel, time, and money. And at high altitudes in high latitudes, the radiation background rises. Astronauts. People in orbit take an elevated radiation dose. During strong surges, the ISS crew moves into the station's best shielded compartments. For future missions to the Moon and Mars, solar storms become one of the chief risks to life itself. Pipelines and long infrastructure. The same induced currents that threaten transformers also flow through long metal pipelines, accelerating corrosion over time and confusing the monitoring systems that track a pipeline's health. It's invisible to the public, but very real to the engineers who maintain it. And here is the part that turns this from a technical curiosity into a policy concern. The grid we have today is not the grid of 1989. It is larger, more interconnected, and runs closer to its limits, which means a severe storm has more long lines to induce currents in and fewer spare margins to absorb the shock. Studies modeling a Carrington-class event striking the modern power network have put the potential economic damage in the range of trillions of dollars, with recovery measured not in days but in months or longer, precisely because those giant transformers are custom-built and there is no warehouse full of spares. That is the worst case, and the worst case is rare. But it is the reason space weather sits on the same risk registers as earthquakes and pandemics. Put it all together, and it becomes clear why space weather is classed among serious infrastructure risks, on par with natural disasters. It is not about one device. It is that modern civilization is a dense web of electrical and electronic systems, and all of them are sensitive to what the sun does. A natural question. Why is all of this happening right now? The answer is in the solar cycle. The sun's activity swings on a roughly 11-year period, from a quiet minimum, when there are almost no sunspots, to a turbulent maximum, when spots, flares, and ejections come in a flood. We are right now at or just past the peak of solar cycle 25, the moment when the sun is most agitated. And here is what matters. This cycle has turned out more active than the early forecasts. More spots, more flares, more ejections. That is precisely why, over the past couple of years, we have seen both the return of G5 storms and auroras at latitudes where they had not been seen in decades. The active region that fired 2 X-class flares in 8 hours is not an anomaly against a quiet sun. It is entirely in character for the phase we are living through. It's worth knowing how unusual the recent stretch has been. The cycle before this one, cycle 24, was notably weak, one of the feeblest in a century, and that lulled a lot of people into thinking the sun was settling into a long, quiet spell. Many forecasts predicted cycle 25 would be weaker still. Instead, it overshot, arriving early and running hotter than expected. The sun has done this before, in both directions. There was a stretch in the 17th century, the Maunder minimum, when sunspots nearly vanished for some 70 years. The point is that our star is not a steady, predictable lamp. It runs in moods, and right now it is in one of its loud ones. The practical takeaway, what we are watching this weekend is not a one-off oddity that will then go quiet. It is a typical product of solar maximum. And until that maximum winds down, episodes like this will keep recurring. One ejection is not the end of the story. And now the thing that worries specialists more than the current ejection. The thing the loud headlines barely mention, because it is not about today, it is about the coming days. The sun rotates. A full turn relative to Earth takes about 27 days. Active regions drift across the visible disk. They emerge from behind the east limb, pass through the center, and disappear behind the west limb. And here the geometry becomes decisive. An ejection is genuinely dangerous to us when it launches from a region near the center of the disk, that is, when that region is facing straight at Earth. Then the cloud flies right at us, head-on. An ejection from a region near the limb usually heads off to the side, missing. The region that produced the current flares has already discharged, but it has not gone anywhere. It is still active, still magnetically loaded, and over the coming days it will rotate, along with the sun, into an ever more Earth-facing orientation. In other words, if it fires again in a day, 2, 3, when it is staring straight at us, the next ejection could be aimed at Earth far more squarely than this one. That is the real worry. Not necessarily the cloud arriving this weekend, which may well graze us or come in with a favorable orientation and hand us mainly a beautiful aurora.